Hello, everybody. I hope you had a good rest of the week and you're enjoying the unusually hot winter. So briefly, we spent the last lecture on two topics. One, we finished model selection, which was the question of how do we estimate the number of principal components in PCA. And the key observations that I made that are related to model selection were that, and I'm writing this because I'll need it today, is that one can do model selection by penalizing the error. Instead of just minimizing the sum of the square of the errors, which is what we usually do, we penalize the complexity of the model. And we discussed how the rank is a good way to penalize it. We discussed various other techniques, such as Bayesian information criteria and others. But I also introduced this alternative way, and the motivation I gave was primarily because it gives a convex problem. So I introduced this nuclear norm as a surrogate for the rank. And as a matter of comparison, I emphasized that if you actually penalize the complexity with the rank, all what you get to do is, probably this was square root, if you recall correctly maybe. All what you need to do is do hard thresholding. You keep the top D singular values of the SVD of the data matrix. Well, the top D is determined as those singular values that are above a threshold, and the threshold is the square root of tau, where tau happens to be the penalty term you put in front of the rank. But I talked also about a soft version of it, where you penalize the nuclear norm. And in that case, the interesting observation was that the optimal solution was the same, except for the fact that instead of using hard thresholding, you do something that is called soft thresholding. And the key difference between the two is that in hard thresholding, you just keep the singular values as they are, while in soft thresholding, you reduce them, you shrink them by tau, and then the ones that are below tau, you set them to. Then, in the second part of the previous lecture, we began talking about how do we do PCA with missing entries. And I started by arguing that if I knew what the subspace is, and I draw a picture that had sort of the subspace and it had sort of a line in it, if I knew what the subspace is, then I could actually find the missing entries by effectively intersecting the known subspace S with the subspace induced by the missing entries. And this is exactly what's written in the equations here, that this is the actually known subspace, the basis, low-dimensional representation plus the point. And this is the subspace induced by the missing entries, because you split the vector into the unknown part and the observed part, and that vector is equal to filling in with zeros what is unobserved, and that gives you a vector that is now known, plus the identity matrix, m by m, m is the number of missing entries here, times the unknown part. Okay, so this gives another subspace, and by intersecting the two, algebraically, I just make the equations equal, and in order, and the unknowns here are the low-dimensional representation and the unobserved entries. And so the number of unknowns is equal to little d, which is the dimension of the subspace, and capital M, which is the number of missing entries. And that's why I need the rank of the basis of the subspace augmented with the columns of the identity corresponding to the missing entries to be number of missing entries plus d. Okay. And we ended up by saying, well, this is equivalent to saying that the number of observed entries, which is the total number of entries minus the missing ones, needs to be at least little d. Right? So in other words, in order to be able to reconstruct a point, a necessary condition is that the number of observed entries is equal to the dimension of the subspace. Okay. Now, all of that, however, was under the hypothesis that I know what the subspace is. So if I give you the subspace, then you can complete any data point. And I try to argue that intuitively, this condition really means that this matrix needs to be full column rank, and therefore it would fail if the missing entries, if the columns of the identity corresponding to the missing entries are linearly dependent with the basis for the subspace. So more broadly, we need some sort of condition that prevents the patterns of missing entries to coincide with what the subspace is. And how do we formalize and make that precise? That's going to be the topic of today's lecture, as well as the important topic of how do I actually find the missing entries in the case where the subspace is not known. Because in this particular case, I will just go ahead and solve the equations, but for that, I need to know the basis, and I need to know the point defining the subspace. So what if I don't know? So first, let me further emphasize the fact that this problem is not going to be always solvable, and what do I need in order for it to be solvable. So first of all of the equations that I wrote here were always just 1 point. Okay. How do I complete 1 point provided that the subspace is known? If I want to actually find the subspace, in the case that is unknown, I need to have many data points, right? Not just one. So the general situation is going to be that the data matrix X that is going to be given to me is going to be a D by N matrix. And some entries will be known, a few of them, throughout all over the place in the matrix, but many others might not be known. Okay, so I have now multiple samples from that subspace. Okay, so let me actually have one particular example that I think highlights the challenges of doing this, of trying to solve this problem, and it highlights the fact that in principle it's almost like an impossible task. So let me give the following concrete example. Suppose that this matrix, that the true matrix that I'm trying to reconstruct was the following matrix. Let me consider that as an example. Okay? And now we're going to play the following game. That's the true matrix, but you don't know it. Okay? So it's not given to any. And all I'm going to do is just sample a fraction of the entries, and those will become the observed entries. And from that fraction that I give you, I'm going to ask you, can you guess what the true matrix was? Okay? And so the question is, can you do that? And so, what is the fundamental issue? The fundamental issue is that if you look at that matrix, right, sample whatever, 90% of the entries, and they have become now observed. Okay. What are those entries going to be? Most likely, with very high probability. All of them are going to be 0, right? And if you keep sampling, imagine now that this matrix was very large. I sort of wrote a 4 by 4 matrix, but imagine that it's 1,000,000 by 1,000,000, and one entry, the entry 1, 1 is non-zero. As you keep sampling, right, 90%, let's say 90%, it's always going to be the case, almost always, that you're going to get the zero entries everywhere. So what is your best guess as to what the true matrix is? Particularly if I tell you that it's the lowest possible rank, right? What is your best guess? Is that it's going to be the all 0 matrix. So how in the world are you going to tell that you have a matrix that has only one entry that is non-zero versus the 0 matrix? Okay. So that's clearly a pathological case of a particular matrix that is going to be essentially impossible to complete. Okay. And so what is the problem with that matrix? The problem with that matrix is that that matrix is not only low rank, but it's also very sparse. Okay. So in fact, if you think about the SVD of this matrix, the SVD, well, not exactly the SVD, but maybe it is. This matrix can be written as such, right? Correct? So it's a rank 1 matrix. But again, think about what we were trying to say here. I don't want columns of the identity of the missing patterns to be linear combinations of the bases for the subspace. Right? That was sort of the situation that made things fail. So here, this is effectively acting as the basis for the subspace. Right? That's the U matrix. And that matrix evidently is a linear combination of, sorry, if I pick the first entry to be missing, right, then it's going to be parallel or identically equal to this U, and so they're going to be linearly independent. So that's example number 1, or failure mode. Example number 2, suppose that the matrix I gave you was now, in fact, let's say it's fully complete everywhere. And now, one entire column is missing. What about that case? Can you reconstruct that extra column? Huh?
Is that column linearly independent with all other columns?
What I mean is, there is a matrix there. It is low rank, but there is one entire column that I don't give you. And the question is whether you can recover that column. Pictorially, it's like what I had here. What was the situation? I actually had a subspace. And I gave you at least one coordinate for that point. That's why all of this line was unknown. Actually, in this particular case, I gave you 2 coordinates. I gave you the x and the y, but the z was not given. And so that's what generated that line, because there was this one-dimensional subspace that was missing. Okay? But at least, because I gave you 2 coordinates, you were able to figure out where this line was and do the intersection. But suppose that I'm putting you in the extreme situation. I give you no coordinate at all whatsoever. What can you do? Well, the fact of the matter is that you've got no information as to where that point might be. And so any point in the subspace is equally good from that perspective. So that's another pathological case where you can't do anything about it. Okay. So what this suggests is that there needs to be sort of 2, it's just intuitively suggesting that there needs to be sort of 2 types of condition. On the one hand, the way in which the entries are missing cannot be sort of pathological. It cannot be the case that I'm missing all of the entries of a data point. That's going to be a failure. On the other hand, the way in which the entries are missing needs to be somewhat different from the basis of the subspace. Okay, and that's somewhat different. I'm going to write right now what it means more formally, and that's going to be the notion of incoherence. Okay. So definition. So x r d by n is nu incoherent with respect to the set of sparse matrices if So this is what the definition says. I'm going to take the the matrix X, and I'm going to compute the singular value decomposition of it. And I'm assuming in this particular case that the rank of X is equal to D. Okay? So I've got a matrix, the matrix has rank D, I compute the compact SVD of that matrix, and I look at the following properties of the SVD. I look at the columns of U, and the two norm, so the maximum over I and the maximum over J. So the two norm of that column needs to be bounded above by some quantity. It needs to be small enough. The two norm of the columns of V needs to be small enough. Actually, this is the rows. Should probably yes. So UI, the ith row of U, and AJ is the j row of U. Okay, so let's try to understand what this definition really means. Okay? So let's consider the SVD. And now let's consider the rows. So 1, U2 transpose, UV transpose, sigma, and likewise here, V1 transpose, Vn transpose. Okay. So if you remember, the matrix U and the matrix V need to be orthogonal. So the columns of them need to be orthogonal to each other. Okay. So in addition, every column needs to have unit norm, right? They need to have unit norm, and they need to be perpendicular to each other. So consider now the following situation that, for the sake of an argument, suppose that the first column was 1, 0, 0, 0. The first column of U was 1, 0, 0. Okay. So in that particular case, can you tell me what this entry is? 0, right? Because it needs to be orthogonal to the first. And likewise, all other entries need to be 0. And the rest, I'm not making any hypothesis for the time being. Okay? But as soon as one of the columns is one of the basis vectors, there needs to be a row that is also a basis vector. Okay? Because of the orthogonality. And what we're doing right now is look at the norms of the rows. So this is a particular case where I'll take this row, right? And the norm of that row will be exactly equal to 1, right? Correct? Now, what about the norms of other rows? Will they be bigger than 1 or less than 1? What do you think? Huh? Let's think about it. Suppose that I had a full matrix that was, square matrix. And let's say that it was orthogonal. What is the sum of what is the norm of every column? 1. What is the norm of every row? Yeah, if it is squared, it's orthogonal in 1, both in the rows and in the columns, right? Okay. What is the U matrix? It's just the compact SVD. So it's really, I had a fully squared matrix U, and I just took a subset of it, right? The top D. Right? So I know the sum of the squares of every row should be equal to 1. What's going to happen if I remove a piece of it? Huh? It's going to be at most 1, right? So I know by construction that it's always the case, in fact, that UI is at most 1. So the case in which the norm of a row of U is the largest is going to be when it is one of the unit vectors. So, and in fact, if the norm is, or at least, sorry, what I meant to say is that one case where the norm would be exactly equal to 1 would be the case that you get one of the unit vectors. The other case is exactly the case where that happened to have zeros to begin with, right? It was already summing up to 1. So once I remove the extra stuff. Okay? So those are the two cases where I'll achieve a case that is equal to 1. So let me now put myself in the other extreme situation. Suppose that this column, instead of being very, very sparse, which is what I've written right now, right? Suppose that it was as dense as possible. And my definition of dense, is more than being dense, it's really being the most balanced. This is sparse and it's very unbalanced in the sense, the sum of the square of the entries needs to be equal to 1. But it's more unbalanced in the sense that I give the 1 to only one of the entries and all of the others are 0. So now, if the sum of the square of the entries is still equal to 1, but it's the most balanced situation, what would that be the case that is the most balanced for that column? The case where all the entries are the same. So if now I've got a situation where all the entries are the same, can I put all of them to be equal to 1? No, because the sum of the squares needs to be equal to 1. So what do the entries need to be? 1 over square root of, how many rows do I have? D. 1 over square root of D, right? Okay. But of course, it doesn't need to be all with ones, right? It could be with +1 or with -1. Agree? So let's say, in fact, that I'm able to build a complete row. And I'm just going to put plus and minuses here. But I guess you believe me that I can build a matrix where all the entries are the same, except for different signs, and they are still orthogonal to each other. All right? Do you believe me that? It's possible. So in that particular case, let me consider one row. What is the norm of that row when all the entries are equal to each other? So in this particular case, that norm of U1 is equal to what? Huh? Little d by
big.
Little d by big D?
Maybe.
Okay. Who disagrees? Square root, right? Because each entry is, so let's consider first sum of the squares, right? The square of this guy is going to be 1 over D, plus 1 over D, plus 1 over D, plus 1 over D. How many times? Little d times. So the sum of the squares of the entries of that row is going to be little d by capital D. But that's the sum of the squares, so I need to take the square root. Okay. All right, so all I'm trying to argue, okay, this was a lot of blah, 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 but I'm just asking the question, what does the norm of the rows of U look like? And I gave you one extreme case where the norm is equal to 1, and another extreme case where the norm is actually less than 1, because D, little d, is expected to be much smaller than capital D. So this number is in principle much smaller than 1. Okay? So in some cases, the rows can be big, and the biggest they can be is 1, but in some cases, the norms of the rows can be small. Okay? And they seem to be bigger, or they are, in fact, guaranteed to be the largest when they are very sparse. And they are smaller when all the entries are approximately the same, plus or minus sign. So if you start looking now at what's written here, magically that D over D appeared over there. Okay? And so what this says is that I want the rows of U to be small. How small? This is kind of this, if I didn't have the nu, this is sort of the smallest possible they can be. Because I could not have a row that was identically equal to 0. Well, I could potentially have one that was identically equal to 0. But the nu parameter therefore controls how small they are. If I select the nu to be very, very large, right, effectively this is no constraint. But if I start to let the nu be smaller and smaller, in particular if I let it to be 1, right, that is sort of getting to this situation where I really want all of the rows to be non-zero and equal to each other and very balanced. Okay? So, therefore, this is sort of a very fancy way of saying that you do not want the rows of U to be sparse. And by analogy, you know, this example, I hope, illustrates the fact that if the rows are sparse, you have to get some columns that are sparse as well. Okay? So, in summary, what does this say? It says that you don't want to have too many columns, or you don't want the columns of U to be sparse. This one says you don't want the columns of V to be sparse. Okay? And why is that needed? Well, let's go back to what I was trying to say. We want the columns of the identity for the missing entries to be, to be incoherent with the columns of the basis of the subspace. So what this is saying effectively is exactly that. I take the SVD, the U matrix gives you the basis for the subspace. Okay? And it's saying, do not let those columns of U to be sparse. Because if they are sparse, you're going to confuse the basis of the subspace with the patterns of missing entries. Okay? And all of the argument I just made is sort of symmetric. Whether it is the basis for this, if I transpose the matrix, it's sort of the same problem. So that's why the requirement is not only in U, but also on V. And I hope that that also illustrates with the example that I was showing over here, right? Because that matrix was one of the critical examples where I was saying the U is very sparse, and that's why it fails. All right? Okay, is that clear now why the definition sort of came out of nowhere, but at least there is some intuition as to where it's coming. Okay. So what does it mean to be incoherent then? The intuition is it means that the low rank part is sufficiently distinct from the sparse part. And why do I care about sparse part? I care about that because missing entries is going to be, selecting one entry is selecting a sparse pattern. Selecting a fraction of the entries is going to be selecting a small fraction of the total number of entries of the matrix. Okay? So what I want to be able to distinguish between these two phenomena is that the low rank part and the sparse part are not too correlated, because if they are too correlated, I will not be able to disentangle the two of them. All right. So with that in mind, let's now move on to an actual formulation of how to solve this problem. So intuitively, what we want to do is the following. So let's X be a low rank matrix. We're going to define this set omega, which is going to be the set of all entries such that Xij is observed. Okay. We are going to define this operator P omega that goes from the D by N matrices to D by N matrix. That does the following: P omega of X is equal to xij if I comma j belongs to omega and 0 otherwise. Okay, so this p omega, all it does is that it takes the input matrix and replaces by 0 the ones that are not observed. Okay, it keeps intact the part that is observed and it sets to 0 what is unobserved. Okay. So intuitively, what we want is, given x, or given actually, we're not given everything, right? We're just given p omega of x. That's the problem formulation. I know the observed entries, that's all I know. What I want to do is find x. Right? That's really the goal. Or this is what we usually refer to as complete x. And all I know is that it's low rank. So here's the way we're going to formulate the problem. We're going to say find a matrix A such that p omega of A is equal to p omega of x. And A is low rank. Right? That's one way to formulate the problem one step closer. Right? What does this mean? This means find a full matrix A of the same dimensions as X and make sure that the observed entries of A agree with the observed entries of X. But for the missing entries, I don't put any constraint because I don't know them. And so going even one step further, what I can now try to say is maybe minimize the rank of A such that p omega of A is equal to p omega of X. And now I actually have a formulation. Okay. Find a matrix of the smallest possible rank that agrees with the entries of the given matrix. Okay, so what type of optimization problem is this? Let's look first at the constraints. The constraints are what? Are linear, quadratic, or convex, non-convex? What are the constraints?
Linear.
Linear. Actually, really what this says, if you just read it right now, this says that Aij is equal to Xij for I, j in omega. Right? So they're remarkably simple. They're linear, of course. But actually, it's just that the values of the entries are known. Right? They're equality constraints, so it couldn't be simpler. So in terms of constraints, this is sort of very trivial. So the only thing that is hard is that, of course, this is minimization over A, is that I need to find the matrix of lowest possible rank. And that's now very nasty. So what we're going to try to do is to relax the problem. And instead of considering the rank, we are going to consider the nuclear norm. So what if we minimize the nuclear norm instead? So now what I have is a convex problem, because the nuclear norm is convex, as you will prove in homework 2. In fact, any norm is convex. So I've got a convex objective subject to linear constraints. But when we do that, a variety of questions arise. First of all, that problem is not convex, and this one is convex. I'm solving a different problem. Are the solutions the same? Or are they not? When is it the case that the solutions are the same? And even if they're not the same, at the end of the day, I don't care about this problem or that problem. I think the more fundamental question is, if I solve either that or this, am I able to perfectly, this is my objective at the end of the day, right? It's like I think of some low rank matrix, I hide it from you, and I give you only a subset of the entries, and I ask you, can you figure out the matrix I was thinking about? And now you go ahead and you solve this optimization problem, you come up with an answer, and the question is that answer the same as the matrix that I had in my head, or not? And that's the part that we care the most. Okay? Now, before I move on to what's going on, let me talk slightly, a little bit more about that problem, because it may not be so familiar to you. And I'll try to relate it to a problem that might be a little bit more familiar. So just to make an analogy, let me consider now the following alternative problem, which is minimize the L0 norm of A subject to well, this is not so the standard notation. Let me try to use a more standard notation. Is the okay. So the L0 semi-norm is just the number of i's such that xi is different from 0. Okay? So that's the number of non-zero entries of a vector. The L1 norm is the sum of the absolute values of the vector. And the absolute value, as you know, as a function, the absolute value of x is equal to x. If x is positive, it's equal to minus x if x is negative. So it's a function like this. Okay? So, what is this problem on the left here? This is, I give you a linear system of equations, or a set of linear constraints, and I said among all possible potential solutions of that linear system, that. Of course, I'm assuming that the solution exists. As you do know from linear algebra, there are cases where this linear system has no solution. There are cases where the solution is unique. There are cases where there is a infinitely many solutions. So I'm sort of considering the case where there are infinitely many, and among those, I'd like to select the one that has that is the sparsest, namely the one that has the smallest number of non-zero entries. Okay? And instead of doing that, because that is a little bit of a combinatorial problem, I search for a solution that minimizes the L1 norm, which is the sum of the absolute values. Okay? So I'm introducing this because I want to make an analogy with the problem we are considering. But just to complete, once you look at a problem like this, you can see that. In fact, let me make a special case. If the x was non-negative, right, the absolute value of x would become just x. Agree? And so what would this problem with the top right be? It would be minimize the sum of the entries of x subject to a linear constraint. That is what type of optimization problem? A linear program, right? Is minimizing a linear thing subject to linear constraints. And so I typically the set of linear constraints might define, for example, this is just an example, a polytope, And if I'm minimizing, I'm just moving the value, and let's say eventually I get to this corner, and that's where the optimal solution is. And for linear programs, we know that the solution is typically in a corner. Okay? Again, this is not an optimization class, and some of you might have taken optimization, some of you may have not. So for those of you who have taken optimization, this is just a little basic refresher. Right? And for those of you who haven't, you have to just believe me. Okay? Okay. So what I want to highlight is that linear programming, even though it's one of the most studied optimization problems, well-known algorithms from the 60s, it has a few peculiarities. And the peculiarities is that you cannot do gradient descent, typically, for example, for linear programs, if you really just try to solve them. Because the gradient, it's a linear function, so the gradient is always a constant, right? And also it has this peculiarity that solutions tend to be in the corners of a polygon. Okay. Now, this adds an extra level of difficulty because we are taking absolute values. And so the L1 norm becomes non-smooth, as you can see from here, right? It's not just a linear equation anymore, but because of the absolute value, there is this point at which the function is not even differentiable. Okay? So, while this problem seems very simple and naive, it has, I'm just trying to say, it has a little bit of challenges and difficulties. Okay? And so what we're going to do now is to even move farther and consider the following thing. What is the rank of A? Well, the rank of A is the number of i's such that sigma I is non-zero, right? If I consider the SVD, what is the rank of a matrix? The rank of a matrix is the number of non-zero singular values, correct? So in fact, I'm going to write the rank of the matrix as I'm going to write all of the singular values of A as a vector, and I'm going to put the 0 semi-norm there, because that's what it is. It's counting the number of non-zero singular values. Okay? So that already establishes a connection between rank and L0 norms. But by analogy, now what is this nuclear norm? Well, the nuclear norm is just the sum of the singular values of A. That's how it was defined, is the sum of the singular values. But that is exactly equal to the sigma A and L1 norm. Because what is the L1 norm? The L1 norm, I just introduced it, is the sum of the absolute values of the entries of the vector. It so happens that the singular values are non-negative. So whether I put the singular values or whether I put the absolute value or not, it's irrelevant. Okay? So the bottom line is that in this standard solving a linear system with sparse solutions problem, what we have done is to replace the L0 semi-norm, which, what is it? Well, it counts things with a 1 if it is non-zero, and it counts things with a 0 otherwise. So if I had to plot it, it's always equal to 1, except that here is 0. So let me just do that. And then it becomes 1 again, right? Negative numbers, I count them as 1. Positive numbers, I count them as 1. And the 0 number, I just give it a 0. So I replace this thing, which is 1, 0, 1, by minus x and plus x. Okay. So by analogy, what's going on here is that the rank of a matrix is something nasty because, as long as the analogy is here, you can make the number bigger or smaller, but the number of non-zero entries doesn't change. In the case of a rank, you can modify linear combinations of things, but the rank might be the same. So, in the same way that the L1 norm is discontinuous, not discontinuous, but non-differentiable at the origin, this nuclear norm, okay, also will have problems with differentiability. Okay? Every time that every time that you have, for example, a rank 1 matrix and you change from rank 1 to rank 2, that's going to be a case where you get an issue of non-differentiability. So this was a long story to try to convince you that the problem on the top left and on the top right, on the one hand, they are extremely simple because the constraints are linear. They are equality constraints, so the simplest possible case. But the rank is non-convex and non-differential. And we're going to replace it by a convex objective, but it is still non-differentiable. And in principle, I cannot just do something like gradient descent, okay, because it's non-differentiable. And so we need to be very careful about how we're going to solve that problem. But for now, I hope it's clearly formulated. It makes sense when we're trying to do it. And so what we need to do now is two things. One is, does this problem make sense? Namely, is the optimal solution to this problem equal to the true low rank X that I started with? Two, how do I actually solve it numerically? So let X be D by N, and assume that the rank of X is D. Let X be nu incoherent. So, assume entries of X are missing uniformly at random. What does that mean? I'm going to have a certain matrix, and now a subset of the entries are going to be missing. And I can tell you one way to do this from a probabilistic setting would be to say, I'm going to define at each entry of the matrix a Bernoulli random variable, that with probability P is equal to 1, and with probability 1 minus P is equal to 0. If it is equal to 1, I keep the entry. If it is equal to 0, I don't keep the entry. Okay? So that's what I mean that they're missing uniformly at random. And this is a way sort of to prevent these weird missing patterns where all of the entries of a particular column are missing for it.
What do you mean by you don't keep it?
Huh?
If it's 0, you don't. What, you said something about not keeping
Okay, so I repeat. There is a true matrix X that is low rank, and the rank is D. From that matrix, I am going to observe only a fraction of the entries. But the pattern of missing entries is going to be chosen uniformly at random. Meaning, what are the locations of the missing entries? Okay? And I made the analogy, this is like at each location there is a Bernoulli, and with probability P, it is kept, and with probability 1 minus P, I throw it off. So, let M be the expected number of missing entries. of observed entries. Observed entries. Okay, so if this was a Bernoulli, right? If really I had a Bernoulli, let me call it Zij, which is equal to 1 with probability, or maybe I should have written it as a Bernoulli. Zij is Bernoulli with probability P, so this means that the probability that Zij is equal to 1 is P, and the probability that Zij is equal to 0 is 1 minus P. So if that was the case, what would be the expected value of observed entries?
P times dn.
Exactly. So this is equal to P and D and that's what I mean by the. So here is, so those are all the assumptions. So this is sort of just exercise. So if M is bigger than or equal to C nu to the 4 dn log of n squared, I think, yeah. Then A star is equal to x. What is A star? A star is going to be the solution to this problem. Okay, so this is the nuclear norm problem. So A star is equal to the optimal solution. With probability one minus n to the minus 3. So let me try to explain what the theorem is trying to say. So if I just start to, so what we're trying to do here is the following. There is a true matrix X that I don't know. I sample this Bernoulli to give you some observed entries. And you go ahead and let's say you had an algorithm that is able to find the optimal solution for that problem. Okay? And now you ask the question, is the result that the algorithm obtained equal to the X or not? So what this theorem says is that if the number of observed entries in expected value, the expected number of observed entries, is above some number, which I'm going to discuss the details of what the number is in a moment. But in a sense it says, if you give me sufficiently many observed entries, then the optimal solution to that convex optimization problem will be unique and will be exactly equal to the low rank matrix that you needed to complete. Namely, you can perfectly complete the low rank matrix with no error whatsoever. Now, the last statement, what it says is that well, you're doing lots of experiments. Every time you generate a new pattern of missing entries. So what it says is that you will be able to perfectly complete that matrix for most patterns of missing entries. Because the probability with which you will be able to do it perfectly is 1 minus n to the minus 3. What is n? N is the number of columns of the matrix. So if the matrix is large, if there are lots of columns, this probability, this term goes to 0. Right? So with probability 1, right, with probability almost 1, you will be able to recover the matrix correctly. In other words, what it really says is that the types of patterns of missing entries for which this algorithm fails is a very small fraction. It's on the order of 1 divided by n to the cube. Okay. So is the statement of the theorem clear as to what is being said?
What are the restrictions on C?
So that's the part of the theorem that I haven't explained yet. Okay. Are we clear yet on what the theorem is trying to say? Okay. That for most cases, if the number of observed entries is large enough, you can perfectly recover the missing entries. Okay. With overwhelming probability is what the last statement said. Okay. So let me now zoom in into what the conditions are. So C is a constant here. Okay, so what really this should be read as M is on the order of whatever follows that. I don't want to say anything wrong here. I believe people have studied what this constant might be, and there might be some papers about it. But I don't know all of the details. So this constant could be large, for example, which could be a bad thing. But I don't know the details. So for the time being, all what the theorem says is that there exists a constant, C, such that if this is bigger than that, then this happens. What are the other pieces of the theorem? So there is this nu to the 4th power. What was nu? Nu was the definition of incoherence. And what I had said earlier was that the smaller the nu, right, the sparser, the smaller the nu, the more dense the rows of u were supposed to be, right? So if nu is large, I am allowing potentially sparse columns of u, and that's a bad thing, right? Our intuition was that the smaller the nu, the better. Okay? And that was my calculation here with dense solution. So here, what this effectively says, if the number of observed entries is bigger than something, so if the nu was large, I need many more entries in order to succeed. But if the nu is small, which means that the matrix is really incoherent, then I need less entries. So that's also explained. Then, this term here. I had said earlier that in order to a necessary condition, in order to complete just one data point, is to observe at least little d entries for that point. If I don't observe any entry, I'm dead. But because the subspace has dimension d, I need to observe at least little d. Because I'm trying to complete not just one point, but n points, what is the minimum lower bound of the number of observed entries that I really need? Well, little d per point. So the smallest possible number would in any case be little d times n. Okay? So what is really remarkable about this result is that the smallest number of observed entries this is sort of the bare minimum just to start talking, right? So what this says is that the lower bound is exactly equal to the minimum modulo this logarithm factor on the size of the data. So there is an extra price to be paid. I need to observe more entries than the minimum to be able to complete it. But the extra factor is just logarithmic on the number of entries. Okay? Is that clear? Any other questions? Yes?
What was C again?
C is a constant. Okay. So in summary, what is the minimum number of entries that are needed in order to complete a matrix? The minimum number is d entries per point up to a logarithm factor and up to a constant factor. And that constant factor is c, that is not very much known, but then the incoherence. Do I know that? I mean, if I give you a matrix, would you be able to verify this theorem? Well, no, because if I give it to you, it will be incomplete. So you don't know whether it's incoherent or not. So you wouldn't be able to compute the nu. And what else you wouldn't know? Well, the theorem also is a theorem in probability. So if you do the experiment a million times, right, for different missing patterns, then in most cases you will get it right. But in practice, I'll just give you one set of missing entries, right? I'll just give you one matrix, and you have to complete it. Okay. So it is really, really, really good to know that this theorem exists, and it provides strong evidence as to why solving that optimization problem is a good thing to do. But it doesn't mean that I will be able to verify it in practice. So in practice, all I'll do is that I'll give you a matrix, you'll run the algorithm, you'll get a solution. Hopefully it'll be low ranked, so that will tell you something about it, but you wouldn't be able to verify it.
Is it log of n square or log n whole square?
Log of n and then square. So if you prefer, I can put the square here. If that's less. Okay. Okay, I'm not going to prove the theorem because it's not so easy to prove. So let me just move to the algorithm as to how we can solve this problem. But for those of you who are in applied math and might be more interested in this, most of the proof really comes from statistics, in particular concentration inequalities. Like the basic of concentration inequality is that you've got a Gaussian, and then what is the probability that x is bigger than something, like a Gaussian. So most of it is concentration inequalities here. Okay, so algorithm now. How can we solve the problem? So what was proposed, by the way, this is a result by Emmanuel Candes at Stanford. And so he also proposed an algorithm, and the algorithm is a little bit of a modified version. So what he proposed to do is minimize the nuclear norm of A plus tau over 2 tau times the nuclear norm of A plus 1/2 the Frobenius norm, such that phi omega of A is equal to phi omega of X. Okay. Why this modification? First of all, I argued earlier when I was introducing the problem that this nuclear norm is not smooth. Okay? So what happens is the intuition that you should have in mind is that this thing really looks like the L1 norm, but I'm adding now the Frobenius squared, which is like this. So once I add them up together, it really looks maybe like this, but now it's smooth there, right? So I fix the problem. Okay, that's the basic intuition as to what's going to happen. But actually, the real reason why this extra term is added is because now, as you're going to see, we're going to be able to solve for A, or at least within the algorithm that I'm going to discuss, in closed form. That being said, however, there is this parameter tau that shows up here. So you should expect the following behavior. If tau is really small, this problem and the problem on the top right are completely different problems. But as tau keeps growing, and if I let tau go to infinity, then this term will dominate that term. And they've shown in the paper that in that case, the optimal solution to this problem will essentially, what happens is that this will produce a solution that depends on tau, and as tau goes to infinity, it will converge to the solution to the problem that we want. Okay? That's the basic equation. So let me tell you now how we solve it and the algorithm to do it. And the fact of the matter is that in MATLAB, you're going to see that with almost like 2 lines of MATLAB code, you can implement now a way to complete matrices. So we're going to use the method of Lagrange multipliers, and so we're going to have tau times A plus 1/2 A for B squared. So I already told you this. How do we handle Lagrange multipliers? It's the objective plus lambda times the constraint. Here, the constraint is a matrix of constraints, but at this point, you should not be scared about matrices of constraints. Right? What do we do? Objective plus dot product between Lagrange multipliers and the constraint. That's what we learned already. So plus the dot product between a matrix of Lagrange multipliers that I'll denote by Z and the constraint, which is P omega of X minus P omega of A. Right? And we always need to write the constraint equals to 0 before we get stuck. Okay? So we are going to be using an algorithm. Let me call this L of A and Z. This is a generic, well-known optimization algorithm that those of you who have taken optimization would recognize, but we'll do the following. We're going to update the primal variable, which is the matrix A, by minimizing the Lagrangian with respect to A with Z fixed. Okay? So in fact, we're going to do something like alternating minimization. We have two variables, A and Z, and we're going to find the primal variable A that minimizes the Lagrangian for a fixed Z. And then we need to modify the Lagrange multipliers. But the issue is that the Lagrangian, as a function of the Lagrange multipliers, is always linear. Right? Because it's always the dot product of the Lagrange multipliers with the constraint. So you cannot just globally minimize that because it's a linear objective. So what we're going to do is just a gradient descent step on Z. So gradient ascent. So the new Z is going to be Zk plus tau, derivative of L with respect to Z, evaluated at Zk. Or AK plus 1, Z. Okay. So that's going to be the algorithm. Find the optimal solution for A, and then take a gradient step on Z. And that's a generic algorithm, by the way. I've written it here for this specific Lagrangian, but this is true in general. Okay? So you have, in fact, it's called the method of Lagrange multipliers. So let me look at that first optimization problem, this one here. So I need to minimize with respect to A. Tau times the nuclear norm of A plus 1/2 A for B squared plus, what else do I have? So you look at this objective. Is this times that, but that's a constant, right? So it's just this times that. So it's really minus the dot product between Z and P omega of A. Okay? Now forget about the fact that this is matrices. Think about it. This is almost like A squared minus A times something. So what I'm going to try to do is to complete the square. Except that I just lied to you a little bit. It's not A squared minus A times Z. There is this annoying P omega forever. Right? Okay, so what is Z times P omega of A? Well, it's the dot product between two matrices, right? What is the dot product between two matrices? Well, we've defined the dot product so that it's easy. So it's just What is the dot product between two vectors? First entry times first entry, plus second entry times second entry, plus. So for matrices we do the same. So this is just the same thing as sum of Zij P omega of A, and then the Ij entry of that, right? All right? And what I'm trying to say here is the following. What is this P omega of yada yada? You keep A the same for the observed entries. And what do you do for the unobserved? You set them to 0. Do you believe me that this is the same thing as setting to 0 the entries of Z and keeping A the same? Because once you put that to 0, it will multiply the other. So whether I put this to 0 or the corresponding in Z, it doesn't matter if I'm taking the dot product. Okay, so there is this, I spelled it out for you this time. But all I was trying to say is that this zeroing out entries of a matrix operator has the nice property that I can move it to the other guy and nothing happens. Okay? It's the same. Whether I set to 0 the entries of A or the entries of Z, it doesn't matter if I'm taking dot product. And so, what that means is that I can move that guy over here. And at the end of the day, what I need to do is to minimize with respect to A, tau times the nuclear norm of A plus 1/2. And now I'm going to complete the square. Because now I've got A squared minus something times A. Okay, so how do you, if these were scalars, how do you complete it? Huh? If I had 1/2 of A squared minus AZ, how would I complete it? Well, it really looks to me that this is A minus Z squared in 1/2, isn't it? Right? Sure, there is, okay, I need to do something like that maybe, but that's a constant and I'm minimizing, so the constant is irrelevant. All right? Is that clear? So I hope you're convinced that this is A minus P omega of Z. Is that right? Just complete the square. All right, so now you will know why I wrote what I wrote at the beginning of the class. Look at what happens here. Given a matrix X, found a matrix E that is close to it, but it also should have low nuclear norm. Given this matrix here, find a matrix that is close to it that has low nuclear norm. Oh, I can solve that problem in closed form. What is the optimal solution? The optimal solution is what? Shrinkage thresholding. So shrinkage thresholding with parameter tau applied to P omega of Z. And so that is the optimal solution to this problem in here. And I apologize that I'm late, but it's just 1 more minute. I'm really done. But this is too nice, right? You have to be patient with extra 4 minutes. All right, so the first step I can do in closed form. And so I'm going to write down AJ plus 1 is equal to shrinkage thresholding applied to P omega of Z. Okay? So given the Lagrange multipliers, I can update the complete rank low rank matrix. And how do I do it? It's super cool. It's just take the matrix Lagrange multipliers, set to 0 all of the entries that are not observed, compute the SVD, and shrink the singular values. And that's going to give you a low rank matrix because you're shrinking, right? Everything that is below the threshold tau will go to 0. Yes?
I'm confused about the 1/2 here versus there was no 1/2 before. Is it shrinkage 2 tau?
I think I have the 1/2 here.
Okay.
And I think I did not write it down in the previous lecture. So you better correct your notes for the previous lecture. That's why this time I make sure to write it down. But in any case, that's going to be the homework, so you will verify whether it's a 1/2 or not. Okay, so is that clear? Matrix of Lagrange multipliers, set it to 0, compute the SVD, shrink, and that's how you get your completed matrix from the Lagrange multipliers. And the next step is update the Lagrange multipliers. So the new zk plus 1 is equal to the old zk plus tau. And okay, this I wrote it fancy here. I went overboard because the derivative of the Lagrangian with respect to the Lagrange multipliers, that's always equal to the constraint, right? So in fact, I shouldn't have done that. What is the constraint? What is the derivative of this with respect to z? Okay, if there were scalars, it would be z times x minus a. So what is it? Exactly that. So this is p omega of x minus a. And I hope you believe me now that whether I take x and set the entry to 0, then take a and set the entry to 0, and then take the difference, versus I first take the difference and then set the entry to 0, is the same thing, right? Doesn't matter. Okay? So those are the 2 lines of the MATLAB code to complete a matrix. And now you iterate, of course.
What do you start with for C?
Brilliant question. So I need to initialize somewhere. And so this is what I'm going to do. I'm going to set Z0, B0 if you wish. But look at what's happening here. Look at this equation. I really want you to pay attention here. This is x minus a, whatever that might be. P omega. So I set to 0 all of the unobserved entries. So if the initial z already has 0 entries at the unobserved ones, this plus that, what property will have? If this guy is 0 in omega complement, this guy is also 0 in omega complement. So the sum of the two is also 0 in omega complement. So as soon as I initialize with any initialization that is 0 in omega complement, this Z matrix will be 0 in omega complement. Okay, so in words, if P omega complement of Z naught is 0, then P omega complement of ZK will also be 0. Okay? So the matrix of Lagrange multipliers will always be 0 in the unobserved entry. So as a consequence, this part here is not even needed, because it's already true by the second step. Okay? So in general, that initialization is enough. But otherwise, you may argue, in fact, maybe I'm going to ask you in the homework to try this out, but I think a better initialization might simply be take the matrix X, fill in with zeros the unknown entries, and compute the SVD and get an initial guess for A. And then initialize A. That's another way. But the fact of the matter is that this objective is strictly convex, okay? And so this algorithm, because the problem is strictly convex, it will be guaranteed to get to the global optimum. And so initialization matters only to the point of will I converge in 1 iterations or in 20 or in 100. That you will always converge.
I guess I have a small confusion about the tau in the objective function.
Yes.
And the tau in the update step. They're not.
Brilliant question. So I don't have the time to explain it because we're out of time for a long time now. But in the appendix, optimization appendix of the book, you will find the explanation. So this augmented Lagrange multiplier method is a very particular optimization method where they have proven the convergence under the assumption that the step size of the gradient ascent is equal to the tau. See you next week.